program. I welcome to our principal Professor Bipin Kumar sir, Professor Ashok Kumar Gupta and faculty members and research scholar from the various institute in international e-conference on chemistry and its application in modern life, jointly organized by Department of Chemistry, Ram Ratan Singh College, Mokama, and Department of Chemistry, Patliputra University, Patna. I would like to thanks to our Honorable Vice Chancellor Professor Jaisawal for giving the to patronizing this event. As we open this one-day international e-conference, it gives us a great pleasure to welcome all of you. In particular, I would like to express my gratitude and warm welcome to our plenary and future international keynote speakers. All of our speakers are very special and have been selected carefully so that all of you can have variety of topics and benefit from their knowledge in the field of higher education and research development in materials chemistry. I also like to show my gratitude to the members of organic committee and core committee for their extended supports. I also thanks Professor Bipin Kumar, Professor Ashok Kumar, presently Head of Department of Patliputra University, Professor Kumar Mangalam, Media Coordinator, Patliputra University, Professor Praveen Kumar, Controller Examination, Patliputra University, Professor Manoj Kumar, Proctor, Patliputra University, Professor S.K. Sahi, Principal A&N College, Patna, Professor Jitendra Rajak, Principal SMD College, Punpun, Professor I.P. Roy, Principal RKD College, Patna, Professor Tapan Kumar Sadil, Principal Commerce College of Patna, and Professor Sanjay Kumar, JN College, Khagol, and Advisory Committee members, Emeritus Professor N.V. Singh, Sharda University, Professor N.V. Singh, UMBC, Maryland, USA, Professor K.D. Mandal, IIT VHU, Professor R.N. Rai, VHU, and Professor Dev Mehto, NIT Patna, Professor Himanshu Sekhar, HOD Chemistry, Veer Kumar Singh University, and Professor R.P.S. Chauhan, Magad University, for their cooperation. I also thankful to technical team, Dr. Sumit Kumar and Dr. Rituraj and Dr. Ryan. I also welcome the teaching and non-teaching staff of the college for great support. The main aim behind organizing this e-conference is provides a forum in which participants obtain knowledge about how the chemistry play an important role in modern life. This program has been designed in such a way that to satisfy the needs of faculty members and academics, research scholars carrying out teaching and research in the field of modern chemistry. As we know that everything is the product of chemistry. In morning we use toothpaste, which chemistry product, and at night when we go to bed we burn a coil, which is also work as a chemical to keep mosquito far from us. This means the chemistry is a valuable subject, and chemistry is everywhere in everyday life, and also it suffocated our modern life. As for chemistry is a fundamental science, and it's talk about the building block elements of the our body, and our body also some digestive system, and our we are using the soap, detergent, all are the chemicals, and the chemistry is present everywhere. So the research is constantly deepening our understanding of chemistry and leading to new discovery. So the chemistry will have to solve many future problems, including sustainable energy and food production. Sustainable energy development, like we are using the lots of electronic devices. We have the lithium-ion battery, capacitor, supercapacitor, solar cell. All are the technology which modern life is depend upon. These are the discoveries and innovation of the chemistry. So faculty members, research scholars interested in applying this technique in the area of interest shall be benefited by the participation. With a large number of participants, we are sure that this e-conference will be memorable, highly educational, and not to be missed event. We hope that this program will help you better understand the subject materials and obtain the knowledge necessary to improve the state of research and education in our country. We truly value your participation and support for this program. Now I request to Professor Ashok Kumar Gupta sir, who is presently the head of department of Patliputra University and also the college inspector of the Patliputra University, and he also has lots of experience in the research and as well as teaching area. So, Professor Ashok Kumar Gupta sir, please, please, I am inviting to you. Please welcome our Vice Chancellor sir, Professor JCR Jaisawal sir, and also our notable speaker. So now, Professor Gupta sir, please welcome to our Vice Chancellor sir.
Honorable VC sir, distinguished guests and participants, good afternoon to all. At the opening of the International E-Conference on Chemistry and its Application in Modern Life, on behalf of the organizing committee, I extend a very warm welcome to all participants in this e-conference. This one-day International E-Conference will enable faculty, students, and research scholars to provide the knowledge on how chemistry changes our daily life. It plays a key role in modern life. Chemistry has contributed significantly to the advancement of human civilization. With a growing understanding and ability to manipulate chemical molecules, chemists have synthesized the crop-enhancing agricultural chemicals to ensure a constant food supply. Chemistry plays a significant role in the eradication of deadly disease by developing life-saving pharmaceuticals and chemical pesticides. Chemists have also developed innovative plastic and synthetic fibers for industrial and consumer application. This International E-Conference aims to provide a global platform to academicians, research scholars, scientists, doctors, and engineers for a wide-ranging, multidisciplinary subjects discussion, meaningful interaction, and innovative ideas from distinguished professors and keynote speakers. This e-conference will be consisting of eminent keynote speech from some distinguished international personalities like Dr. Nanasaheb Thorat, Marie-Curie research scientist, Oxford University, UK, Dr. Nem Singh, research professor, Korea University, Seoul, South Korea, Dr. Rabindranath Lo, associate scientist, Czech Academy of Sciences, Czech Republic. I welcome all of them. I am pleased to welcome VC sir to this International E-Conference. Honorable Professor Gulab Jaisawal, the Vice Chancellor of Patliputra University, is M.Com and PhD from Banaras Hindu University. Honorable Sir is Professor of Finance in the Faculty of Commerce, BHU since 2006. Before joining BHU, he was Professor and Head Department of Financial Studies, Faculty of Management at Purvanchal University, Jaunpur. Honorable Sir has been the recipient of various awards such as Letter of Appreciation by several organizations. He was also a Vice Chancellor of Faizabad University in UP and Nalanda University in Bihar. Honorable Sir has been also awarded as a Commandant Colonel in Faizabad University. Apart from this, he has more than 27 of teaching and research experience, has published about 35 research papers in various national and international journals, written 4 books and has more than 50 papers to his credit, which he has presented in various conferences, seminars, and symposium. Patliputra University is moving towards a successful path under direction of our Honorable Vice Chancellor, sir. I would like to request Honorable Professor Gulab Chand Ram Jaisawal, the Vice Chancellor of Patliputra University, to say few words to our participants. Sir, please say some words.
सबको नमस्कार। इस इंटरनेशनल ई-कॉमर्स conference on chemistry and its application in modern life. This is a very relevant topic nowadays, even in the corona period. And the organizing principal of the college, Professor Bipin Kumar ji, and Professor S.P. Sahi, the principal of the IN college, Professor Tapan Shandinle, the principal of the Commerce College, and Professor A.K. Gupta, the head of department, PG head, Department of Chemistry, Patliputra University, Patna, and the convener of the conference, Dr. Nem Singh, head of Department of Chemistry, RR College, Mokama. The secretary of the conference, Professor Kumar and Professor Praveen Kumar, Professor Manoj Kumar, the chief proctor of the university, and joint secretary of the conference, Jitendra Kumar Ajak, Professor I.P. Roy, principal of the Arcade College, Patna, and Professor Sanjay Kumar, the principal of the JM College, Khagol, and the most important thing, the keynote speaker from the abroad, Dr. Nanasaheb Thorat and Dr. Nem Singh, the research professors, Korea University, Seoul, South Korea, and Dr. Rabindranath Lo. And there is also a various member of the advisory committee as well as the core committee and organizing committee of the conference and print and electronic media. I welcome you all on behalf of the University, Patliputra University, in the eve of the new coming year, that is 2021, very soon. So the topic concern is a very relevant in the present scenario कि रसायन शास्त्र का आधुनिक जीवन में क्या महत्व है, क्या उपयोग है, जिसकी अनुभूति हम लोगों ने अभी बहुत, जो कोविड पीरियड अभी चल रहा है जिससे हमारा पूरा विश्व संक्रमित है, अभी भी है, एक दूसरे तरह का जो स्ट्रेन क्या कौन सा कोरोना का रूप जो लिया है, ब्रिटेन में भी लिया है और भी कुछ कंट्री प्रभावित हैं। अब इनके इम्पैक्ट फैक्टर को भी एसेस कर सकते हैं कि जो वायरोलॉजी टेक्नोलॉजी है या जो लैब है उसके माध्यम से हमारे देश के साइंटिस्ट इसमें भी लगे हुए हैं। ब्रिटेन में तभी इसको डायग्नोसिस कर ली गई है, उसका भी खतरा भी हम लोगों के ऊपर मंडरा रहा है। और ऐसे परिवेश में हमारे पूरे विश्व का जो जीवन है, मॉडर्न लाइफ है, किस तरह से हम सरवाइव कर पाएंगे और इस केमिस्ट्री के माध्यम से हम इसको एसेस कर सकते हैं कि इसका मानव के जीवन पर और हमारे समाज पर क्या प्रभाव पड़ेगा। निश्चय ही यह जो कन्वीनर लक्ष्मण सिंह के द्वारा इस तरह का और हमारे पीजी हेड गुप्ता जी के द्वारा ऑर्गेनाइज किया गया है, हम इनके लिए अपने विश्वविद्यालय से हम बधाई देते हैं। पीपीयू के रसायन शास्त्र विभाग और आरआर कॉलेज मोकामा के संयुक्त तत्वाधान में आयोजित विद्वानों का हम स्वागत करते हैं। और वक्ता के रूप में जिनका हमने अभी नाम लिया है, नाना साहेब थोराट और कोरिया विश्वविद्यालय के नेम सिंह और चेक गणराज्य के वैज्ञानिक डॉक्टर रविंद्रनाथ लो और जितने भी हमारे विश्वविद्यालय के विभिन्न समितियों में विद्वान हैं, हम सबका हार्दिक अभिनंदन एवं स्वागत करते हैं। वैसे तो विस्तार से तकनीकी दृष्टिकोण से वक्ता गण इस पर विशेष प्रकाश डालेंगे, लेकिन मेरी दृष्टि से इनका 5 उपयोग हो सकता है। इससे अतिरिक्त भी हो सकता है, चूंकि जो हमारे कीनोट स्पीकर हैं इसके बारे में विस्तृत जो वैज्ञानिक हैं चर्चा करेंगे। पहला उपयोग जो है समन्वयवादी दृष्टिकोण, इसी तरह से दूसरा जो है तथ्यपरक जीवन दर्शन, और तीसरा है कि व्यवस्थित जीवन शैली। चौथा पॉइंट है कि अणु परमाणु का महत्व, अर्थात छोटी छोटी बातों का महत्व। और पांचवा जो कंक्लूडिंग है कि किस तरह से हमारा जो कंक्लूडिंग थिंकिंग है, किस तरह से इस 5 भागों में हम इसको बांट सकते हैं। जहां तक समन्वयवादी का तात्पर्य है कि आधुनिक और प्राचीन काल का कैसे हम किस तरह समन्वय करते हैं, जो जेनेसिस ऑफ केमिस्ट्री है और जो मॉडर्न युग की केमिस्ट्री है, जो हम कहते हैं कि ऑर्गेनिक इनऑर्गेनिक बहुत पहले सुनते आ रहे हैं। मेरे ख्याल से इसमें इंडस्ट्रियल केमिस्ट्री भी होती है, बहुत सारी केमिस्ट्री है, कई भागों में इसकी ब्रांचेस सब हो चुकी हैं, क्योंकि दैट इज एरा ऑफ द स्पेशलाइजेशन और देयर इज अ नीड ऑफ द different type of specializations to prepare special cadre of scientists in the area of the science concern. तो इस सबको मिलाकर हम इसे कहते हैं कि इसी से हमारा रसायन बनता है। और रसायन की जहां तक बात है, हम काशी के रहने वाले हैं, बनारस, तो बनारस की बात करते हैं तो इसमें भी रस है, इसमें भी केमिस्ट्री है। जो काशी की केमिस्ट्री है, जो लॉर्ड शिव की नगरी है, इसकी भी एक अनोखी कह सकते हैं कि प्राचीन काल से चला रहा यहाँ लॉर्ड शिवा का मंदिर, और आधुनिक जो आधुनिकता का और नई टेक्नोलॉजी का जो मिसाल कहते हैं, इस काशी में देश विदेश सारे विश्व के लोग आते हैं। और इसकी अद्भुत माया को जो है बनारस में ही उस तरह कहते हैं कि कहीं न कहीं इसकी केमिस्ट्री जो है बनारस की, उसमें कुछ अद्भुत चीज है जिसमें हनुमान जी की विशेष कृपा है। यहाँ एक संकट मोचन मंदिर है काशी हिंदू विश्वविद्यालय के पास, जिसको कहते हैं कि मानस नगर में है, कि गोस्वामी तुलसीदास जी ने यहाँ पर भगवान हनुमान जी का दर्शन किया था, और इस मंदिर की स्थापना में कहीं न कहीं उनका जो भी कहेंगे किसी न किसी रूप में उनका जो है इसमें योगदान रहा, जो भी रहा, क्योंकि तुलसी घाट पर बैठ के इन्होंने रामचरितमानस की रचना किया। और राम के जो परम भक्त कह सकते हैं, परम हनुमान जी ही रहे हैं, क्योंकि कहा भी जाता है कि राम जी का भी काम बिना हनुमान के नहीं चलता है। इसलिए बिना केमिस्ट्री से हमारे जीवन लाइफ में या हमारे लाइफ को व्यतीत करना बहुत ही कठिन है। हमारे जीवन में कहते हैं कि राम रसायन तुम्हारे पासा, हनुमान जी के पास राम रूपी रसायन, राम रसायन तुम्हारे पास, सदा रहो रघुपति के दासा। तो ये देखिए हनुमान चालीसा में भी कहा गया है कि हनुमान राम रूपी केमिस्ट्री कहीं न कहीं लोगों के जीवन में जीवन के मूल्यों को प्रभावित, व्यवस्थित जीवन शैली को, तथ्यपरक जीवन दर्शन को, हमारे छोटी छोटी बातों में महत्व इसलिए रखती है कि एक राम ही हमारे आदर्श हैं, जिनके हम आदर्श को लेकर इनको मर्यादा पुरुषोत्तम राम कहते हैं। हम अपने जीवन शैली को, अपने जीवन में संस्कृति और जो कहते हैं कि जो भी आचरण है, जो भी चरित्र की वैल्यू है, इससे हम अपने जीवन को कहीं न कहीं सुंदर बना सकते हैं, सुव्यवस्थित बना सकते हैं, संस्कारित बना सकते हैं, जिससे हम जीवन में शाश्वत और नैतिक मूल्यों की बात करते हैं। ये सभी के लिए उपयोगी है, चाहे वो साइंटिस्ट हो, चाहे वो टेक्नोक्रेट हो, चाहे वो प्रोफेशनल्स हो, किसी फील्ड का भी कोई व्यक्ति हो, राम रूपी केमिस्ट्री या राम रूपी रसायन सभी के लिए जरूरत है। बिना केमिस्ट्री के हम भोजन नहीं करते हैं, तो उसकी भी एक केमिस्ट्री अलग है। तो डिफरेंट तरह की केमिस्ट्री है, और जिसके बारे में लक्ष्मण सिंह है, विशेषज्ञ हैं, विदेश भी काफी रहे हैं, और ये सारे जो ऑक्सफोर्ड यूनिवर्सिटी से विद्वान जन आए हैं इसमें अपने विचार रखेंगे। दूसरा जो तथ्य पूर्वक जीवन दर्शन के महत्व है, हम जो भी वह तथ्य आधारित हो, आधारहीन बातों का जीवन में महत्व नहीं होता है, कि किसी न किसी बात का कोई आधार होना चाहिए। जैसे हम अभी मैं बनारस के बारे में बताया, इसी तरह से नालंदा की जो संस्कृति रही है, कोई न कोई इसका इतिहास तो रहा है। तभी तो इतिहास के बारे में बताते हैं कि नालंदा विश्व की शिक्षा का केंद्र रहा है, और उसकी जो शिक्षा का जो बिंदु रहा है, पाटलिपुत्र का इतिहास रहा है, वैशाली का रहा है, मगध का रहा है। निश्चित इतिहास में इसका कहीं न कहीं हर तरह से साइंटिफिक दृष्टिकोण से देखें, चाहे किसी राजनीतिक दृष्टिकोण से देखें, आर्थिक दृष्टिकोण से रखें, किसी व्यवस्था को चलाने के लिए हर तरह के दृष्टिकोण की जरूरत होती है। इसलिए हम जीवन मूल्य उस समय चाणक्य के समय में कैसा था, पाटलिपुत्र का, मगध का क्या इतिहास रहा, कहीं न कहीं इन छोटी छोटी बातों का भी हमारे जीवन महत्व है। व्यवस्थित जीवन शैली आज के लिए बहुत ही जरूरी है, क्योंकि हम भागम दौड़ी के जीवन में हम अपने लिए कुछ भी नहीं कर पा। साइंटिस्ट है तो हम 24 घंटे रिसर्च में ही लगे रहते हैं। हम अपने लिए कितना समय निकालते हैं, ये बहुत इंपॉर्टेंट है, क्योंकि हम जिस प्रोफेशन में हैं, किसी को पैसे की भूख है, तो किसी को रिसर्च की भूख है, तो किसी की मूल्यों की भूख है, क्योंकि नाना प्रकार के, क्योंकि कहा भी गया है कि एक पिता के 5 कुमारा, पृथक पृथक कोई गुण असारा, कोई पंडित कोई तापस ज्ञाता। मतलब कोई कहने का तात्पर्य गोस्वामी तुलसीदास जी ने कहा है कि 5 उंगलियां हैं, 5 लोग हैं, तो हर में कुछ न कुछ विविध गुण होते हैं, और ये हम केमिस्ट्री के माध्यम से इसको टेस्ट कर सकते हैं। तो इस तरह से केमिस्ट्री का यहाँ भी उपयोग है। इसी तरह से अणु परमाणु की तरह भी जीवन में छोटी छोटी बातों का महत्व है, जिसको हम रसायन विज्ञान में सीख सकते हैं, क्योंकि लैब में यही सिखाया जाता है कि जो चीज जहां से उठाओ पुनः वहीं रख दो। इसी तरह की जो है कार्य केमिस्ट्री के माध्यम से, चाहे डिफरेंट तरह केमिस्ट्री है, चाहे हम साइंस के क्षेत्र में ही बात करें, पहले बीजेडसी होता था, आज बीजेडसी के पता नहीं बॉटनी, जूलॉजी, केमिस्ट्री के कितने पार्ट, माइक्रोबायोलॉजी हो गया है, तो बायोकेमिस्ट्री हो गया है, इतनी स्पेशलाइज्ड एरिया हो गया है कि आज आधुनिक काल में हर फील्ड में कहीं न कहीं जो है ये टेक्नोलॉजी और शिक्षा के क्षेत्र में या विज्ञान के क्षेत्र में, जैसे हम चंद्रयान की ही बात करते हैं, कितने स्पेस साइंस की ही बात करते हैं, हमारी साइंस इतनी आगे बढ़ चुकी है कि हम जिससे टेक्नोलॉजी के उपयोग से कहीं न कहीं हम अपने उद्देश्य को, अपने देश का नाम विश्व में जो डंका बजाने काम करते हैं। अंत में सोच से अभिप्राय यही है कि जीवन का हर काम कोई न कोई निष्कर्ष होना चाहिए, क्योंकि गीता भी हमें बताती है कि कर्मणे बाधिकारस्ते महाफलेषु कदाचन। गीता की भी हम केमिस्ट्री पढ़ेंगे, जब भगवत गीता की पढ़ेंगे, व्यास जी ने जो मंत्र दिया है कि कर्म को ही प्रधान माना गया है, हमें फल की इच्छा नहीं करनी है, जो मूल मंत्र है। हम इस निष्कर्ष पहुंचते हैं कि हम जो भी रिसर्च करते हैं, हम उसके कार्य के बारे में चलें। जब हम अच्छा कार्य करेंगे, अच्छा एक्सपेरिमेंट करेंगे, तो उसका साइटेशन इम्पैक्ट फैक्टर, लास्ट में हम जो कहते हैं कंक्लूडिंग रिमार्क, अपने आप ही अच्छा होगा। उसी के आधार पर हम अपने पेपर को, चाहे वो सेल बायोलॉजी हो, चाहे नेचर हो, चाहे डिफरेंट तरह के साइंस के फील्ड में जर्नल है, हम उसमें अपने पेपर को पब्लिश करा करके अपने साइटेशन इंडेक्स को, अपने जो है साइटेशन को कहीं न कहीं हम आगे कर सकते हैं। ऐसे विद्वानों का मैं सम्मान करता हूं कि ये बहुत ही अच्छा टॉपिक रखा है, और जिसका उद्देश्य यही है, सबसे जरूरी है, रिलेवेंट है कि इस मॉडर्न लाइफ में इस केमिस्ट्री का क्या उपयोग है। इसलिए क्योंकि एक रसायन शास्त्र अपने अनुसंधान के बाद किसी न किसी निष्कर्ष पर जब पहुंचता है, तभी तो हम सत्यपरक बात कहते हैं। और ये सारी बातें हमारे आधुनिक जीवन के निर्माण में अत्यंत ही उपयोगी हैं, जिसका संबंध कहीं न कहीं रसायन शास्त्र से है। इसलिए आज इतने शानदार विषय पर, आज का जो विषय है, इतने प्रासंगिक विषय पर जो वेबिनार, अंतर्राष्ट्रीय वेबिनार का आयोजन मोकामा कॉलेज और हमारे विश्वविद्यालय के द्वारा गुप्ता जी और लक्ष्मण सिंह के तत्वाधान में या इनके सहयोग से जो किया गया है, इस छुट्टी के दिनों में विंटर वेकेशन हम मना रहे हैं। और एक्सपोर्ट में भी मेरे ख्याल से विदेशों में भी ये तो मनाया जा रहा होगा, क्योंकि नाना साहब जो है 25 तारीख के बाद ही वहाँ पर बड़ा धूमधाम से मनाया जाता है। लेकिन कोरोना के कारण कुछ ये कार्यक्रम लिखे हुआ है, लेकिन फिर भी इस तरह का पठन पाठन और इस तरह का अंतर्राष्ट्रीय वेबिनार करना एक बहुत ही हमारे लिए उपलब्धि की बात है। निसंदेह हमारे समाज में जो विभिन्न तरह के लोग हैं वो इससे लाभान्वित होंगे। इसके लिए मैं अपने विश्वविद्यालय के तरफ से आप सभी को बहुत बधाई देता हूं। और बहुत जल्द ही हमारा 3-4 दिन बाद फ्राइडे से हमारा नव वर्ष शुरू होने वाला है। इसके भी हम सभी के मंगल भविष्य की कामना करते हैं। जय हिंद, जय भारत।
धन्यवाद सर। आपने जो रसायन शास्त्र पर इतना सारा कुछ मतलब वो हम लोगों को दिया, तो रसायन शास्त्र रियली अमेजिंग जो मतलब विषय वस्तु है उसका हम जो है आपने जो है कोविड-19 के बारे में जैसे कहा था, तो हम जो अभी जो 3 हथियार जिनको हम मानते हैं, चाहे वो मास्क हो, चाहे वो सॉफ्ट डिटर्जेंट हो, सैनिटाइजर हो, ये अपने मॉडर्न लाइफ में बहुत ही ज्यादा उपयोगी है, जिससे हम इस समय जो है कोरोना वायरस और बहुत सारी चीजों से हम लड़ रहे हैं। जैसे मास्क जो होता है वो 90 N95 और बहुत सारे तरह के जो मास्क हैं, वो सारी चीजें जो है विषय वस्तु जितनी भी हैं वो सब रसायन शास्त्र से ही जुड़ी हुई हैं। डिटर्जेंट है, सॉप है, बिकॉज हम लोग जानते हैं जो वायरस सेल जो होती है उसकी जो लिपिड लेयर जो होती है उसको डिस्ट्रॉय करने के लिए जो साबुन में जो एलिमेंट होते हैं वो सारी बारीकियां जो है हम लोग जो है केमिस्ट्री से और रसायन शास्त्र से ही सीखते हैं। सर जो हमारे बहुत ही विद्वान सर हैं जो कॉमर्स फैकल्टी से हैं, उसमें भी जो है हम लोगों का भी एक केमिस्ट्री डिपार्टमेंट जो BHU जो है वो पूरे ऑल ओवर वर्ल्ड में वहाँ के जितने भी एलुमनी से लेकर सब जो हैं तो बहुत ही विद्वान लोग हैं। रसायन शास्त्र के बारे में मैं बताना चाहूंगा, हमारे यहाँ जो है प्रोफेसर CNR राव, जैसे सर ने अभी कहा था कि रसायन शास्त्र के इस समय जो है मॉडर्नाइजेशन में जो है बहुत सारी विषय वस्तु हो गई है। जैसे फिजिकल केमिस्ट्री हो गया, इनऑर्गेनिक केमिस्ट्री हो गया, और आपका नैनो मटेरियल्स नैनो साइंस हो गया, मटेरियल केमिस्ट्री हो गया, मटेरियल साइंस हो गया। तो जो मटेरियल साइंस वगैरह, मटेरियल केमिस्ट्री वगैरह है और नैनो मटेरियल्स और नैनो टेक्नोलॉजी जो है, जो हमारे जो है अभी जो प्रोफेसर CNR राव जो भारत रत्न भी रह चुके हैं और जो प्रधानमंत्री के सलाहकार रहे थे, वो भी हम लोगों के यहाँ BHU के एनुअली रहे हैं। और उन्होंने जो है इसमें जो है नैनो मटेरियल्स और नैनो साइंस और नैनो टेक्नोलॉजी में काफी काम किया है। जो मटेरियल्स साइंस का बहुत ही जो है ऑल ओवर वर्ल्ड में हम लोगों का है। और प्रोफेसर भटनागर सर जो कि BHU के एलुमनी रहे थे केमिस्ट्री के, जिनके नाम पर अभी जो साइंस का जो भटनागर प्राइज दिया जाता है, तो केमिस्ट्री जो है वो हर जगह मौजूद है। कुछ रसायन शास्त्र में हम लोग जान रहे हैं, जैसे कि जो मास्क होता है उसमें जो है हम लोग जो यूज करते हैं, तो कुछ लोगों का जो है हम जब जाते हैं या बाहर निकलते हैं तो बहुत लोग हम लोगों से पूछते हैं कि जो मास्क जो होता है सर, हम उसका उपयोग क्यों करें, बिकॉज समटाइम्स दे हैव ए थ्योरी अबाउट लॉट्स ऑफ थ्योरी अबाउट दैट, बिकॉज जब वायरस जब इतना नैनो साइज में है तो हम लोग जो है उसको जो है कैसे बचा सकता है। एक्चुअली क्या होता है कि उसमें एक वायरस लोड जो होता है वो महत्वपूर्ण होता है कोविड-19 से बचाव के लिए। तो ये सारी चीजें जो है रसायन शास्त्र की उससे ही सीखी जा सकती है। तो मैं ज्यादा प्रकाश में डालते हुए जो हमारे जो ऑक्सफोर्ड यूनिवर्सिटी से जो है रिसर्च है डॉक्टर नानासाहेब थोराट, जो कि इसमें कोविड-19 में जो है काफी कुछ काम किए हैं और उन्होंने जो है बहुत सारी चीजों पर जो है इस सिचुएशन में काफी सारा काम किया है। उन लोगों ने भी हम लोगों को समय दिया, क्योंकि इस समय जैसे सर ने बताया कि 25 दिसंबर के बाद जो है हम लोगों ने काफी लोगों से जो है विचार विमर्श किया था, लेकिन जो उधर जो है यूरोप से लेकर वेस्टर्न जो जितना भी हुआ है वहाँ जो है क्रिसमस से लेकर जो है न्यू ईयर का हॉलीडे चल रहा है, लेकिन इन लोगों ने हम लोगों को जो समय दिया वो बहुत ही वैल्यूबल है। तो मैं ज्यादा प्रकाश से डालते हुए मैं जो है मैं सर का बहुत बहुत धन्यवाद दूंगा, वाइस चांसलर सर का। और मैं सबकी परमिशन से इनवाइट करना चाहूंगा कि अपने जो टुडे के जो पहले स्पीकर है डॉक्टर नानासाहेब थोराट को इनवाइट करूं।
लक्ष्मण जी,
यस सर।
एक सेकंड थोड़ा रुकिए, सर को धन्यवाद देते हैं।
जी जी सर।
Thank you so much, sir. We are really thankful for your kind address and auspicious presence at our program, sir. We are honored and excited for your participation in our program and obliged for giving valuable time from your schedule. Thank you so much, sir. Now I hand over the mic to Dr. Laxman Singh, HOD Chemistry, RRS College, Mokama, convener of the conference. Please introduce today's eminent speaker of this session, Dr. Nanasaheb Thorat, Marie-Curie Research Scientist, Oxford University.
हाँ, थैंक यू वाइस चांसलर सर एंड थैंक यू गुप्ता सर। सो हम लोग जो है ज्यादा समय ना वो करते हुए हम लोग डॉक्टर नाना साहब थोराट को बुलाएंगे। सो सर, Dr. Nanasaheb Thorat is outstanding experienced researcher currently working as a Marie-Curie Fellow Research Scientist at the University of Oxford Medical Science Division. Dr. Thorat is a two-time winner of World Most Prestigious Fellowship, Marie-Curie Fellowship, and also working as Evaluation Panel member of Marie-Curie Fellowship Application for Life and Engineering Science since the year 2019. Dr. Thorat has published peer-reviewed journal research papers and articles, 1 international and European patent filed, 2 European innovation and invention registered, 5 book, 10 book chapter, presented 5 keynote speeches, 15 invited lectures, and 5 oral presentation at prestigious scientific conferences in Singapore, France, Germany, USA, Ireland, Poland, South Korea, and India. Received international acclaim and awards for research contribution, generated research fund in 6.5 crore, supervised student, junior researcher, and actively participated in outreach and scientific dissemination for the service of the wider community. Dr. Thorat is the first Indian awardee of the European Commission Innovation Radar Grand Prix of the Innovation Radar Prize 220 and many other national and international acclaims on his name. Dr. Thorat is also winner of other prestigious fellowship, including the Japan Society of Promotion of Science Fellowship in Japan, PVC Outstanding Fellowship, Israel 2016, and also worked as Senior Research Fellow at Samsung Biomedical Research Institute, South Korea 2014 to 2015. At the University of Oxford, he is working in the Medical Science Division jointly with the Engineering Science Division. His current research work involves designing new light activated nanomedicine therapy and Raman imaging techniques for brain cancer of pediatric. So I am inviting Dr. Thorat. Dr. Nanasaheb Thorat, are you there?
Yes, yes. Thank you very much, Dr. Laxman Singh, for inviting me to give a keynote talk in your conference. And first, I would like to thank you very much, the Vice Chancellor of the University, Patliputra University, being with us and his guidance. Also, I would like to thank Dr. Kumar sir with us, and she gave us a valuable information about the chemistry and the overall life. First, I would like to, give the idea that I am not belong from directly the chemistry part, and I have my master in physics and even PhD in physics, and currently I am totally in the medicine field. But as you all know, chemistry is a living life science part. Though we have divided our science in different streams, physical, chemical, and life science. But my inspiration is that if we consider our body, our human body, let's say, and if we think about in the way of science, it can be just a physics because it has an energy everywhere in the body, and physics deals with the energy. It can be a biology only, because biology deals with in very nano level, like DNA or proteins, and now virus is there. And when we come to the chemistry, I would say our whole body is just chemicals. So they have the atoms and molecules, even DNAs and their nucleotides. They consist with the just atoms and molecules, and they are from carbon, nitrogen, oxygen. So our body is just a mixture of chemicals, and they are arranged with respect to the energy. So using the physical forces, so we can be drive the biology. So like we are the living organism. So these three streams of science, they are interconnected, they are interdisciplinary. And I myself have physics degree in MSc and in PhD though. I'm completed in medicine, but I'm using still bridge of chemistry to transfer my physics knowledge into the medicine. And that I will explain in my presentation. In a short presentation, I will not take you a long time. What we are doing here and what is my research area and what actually in Oxford what we are doing and some part of my previous research. So in the Oxford, I belongs to the medical science division. Though my work is in medicine, I am also a part of the chemical engineering department in Oxford University. And we are working on the nanotechnology and nanomedicines for the cancer therapeutics. Not only cancer, but we are working on the infectious diseases. So after the pandemic, coronavirus pandemic, everybody knows about the infectious diseases. There were two infectious diseases. Generally, we can categorize. One is by the viruses and one is by the bacteria. So we are working on the deadly bacteria as well. Those have the drug resistance or antibiotic resistance. And as you know, now Oxford is very famous in India because of their vaccine development. And our medical science division, we have the 21 departments. So the vaccine department is one of the part of our division. I belongs in the women and reproductive health department, but our more departments are like I'm more focused on the oncology department, and we are delivering, not directly dealing with the vaccines but we are designing the liposomes for the vaccine deliveries now. So probably you may have heard about the Pfizer vaccine. They are using the liposomes, and they are just lipid bilayers, chemicals, which are used for the delivery of vaccines into the appropriate immune cells. So Oxford is situated in the England. England, we call it is a Great Britain or Britain. It is just 1 hour from the London. Oxford is a very small city, and it is just a university city, we call. So here in Europe.
University
Hello. Yeah. So our university or the universities in the Europe, they are more on, they don't have their own campuses, so they are everywhere in the cities. Okay. So like our Indian universities, they have their own campuses somewhere in the city, outside of the city. But here, all universities, they have everywhere in the city. So like Oxford has also the same. So they have the campus everywhere in the city. So we can't distinguish where is the city, where is shops, where are malls, and where are the university buildings. So Oxford is everywhere in the city. There were two universities. One is Oxford University and Oxford Brook University. But Oxford Brook is a small university and they have their own campus. But Oxford is everywhere in the city. And my department is situated in the main city, but our main lab is outside the city because it is a new engineering lab. So Oxford has a great history. It has a history for around 1200 years, and they have top university in the world from last some couple of years because of their research and spin-off activities. So not only just doing research, Oxford has produced big alumni, like they have many 14 countries prime minister were educated from the Oxford University, and even Indira Gandhi, Manmohan Singh, they were educated from the Oxford University. Like Bill Clinton or Bill Gates, and more than 28 UK's prime minister were educated from the Oxford. Right now, Oxford has produced 80 Nobel laureates, and even our department has 2 Nobel laureates. They are working every day in the department. Right now, more than 40 Nobel laureates are directly teaching and doing research in the Oxford. We have our technology transfer unit, and every year Oxford is publishing more than 10,000 papers, but they are publishing or patenting more than 500 patents every year. So not just doing research on lab scale, but technology transfer is the more part. And that's why we got the vaccine, because it is a vaccine is developed by the one small spin-off jointly by the Professor Sarah Gilbert, who discovered this vaccine in vaccine department, Jenner Institute we call, in the Oxford. So with this brief introduction, I will come to my today's talk. And though I am working in the Oxford University, I get funded by the European Union, European Commission. And I'm not just funded by the European Commission, I'm also working as a management council member of the European Commission's cooperation in science and technology. So we are not just in the doing research in the lab, but I am the policymaker for involved in the policy making of European Unions. Especially I am more on the cancer side. So from the next year, like from 1st of January, Europe is launching new funding scheme called Horizon Europe. So, and I am the member of that policy making. So I will be there for 2028 to design the policy making for cancer and how we can beat the cancer in Europe and across the globe. So parallelly, we are doing the research in the lab, and in parallel, we are working in policy making as well, and even other scientific activities. So we have our cancer plan, beating cancer plan, and what we design, what our policies in Europe is that even all countries across the globe, they have the similar policies. So first is the try to prevent the disease. If we can't prevent it, try to diagnose the disease. Once we diagnose, design the treatment, and with the treatment, make the quality of life of patient and survivors happy, or to improve the quality of life. So this is overall plan for everyone. Unfortunately, though we have a plan, though we have research and developments, we got failed in this disease, because cancer is not just like a viral disease which is coming immediately and going immediately as well with vaccines or drugs. Cancer is evolving from last 1,000 years, and it might be in our community for, we don't know the future when it will be going out to the society. So it's dangerous, still dangerous, and still second most leading cause of deaths. It's not, we can't just hypothesize why we get cancer. It's because of genetic mutation, because of the changes in our body, or because of environmental factors. So they all come together. Some cancers, they are genetic, but their percentage in the overall cancer scenario is less. But some cancers are because of our food habit, our lifestyle, and environment. So we need to be bother and focus on this. Right now, we don't have just single or 2 or 3 types of cancers. We have more than 100 types of different diseases coming together, and they are developing cancer in our body. And we have more than 50 types of cancers, from brain to our skin. So it's kind of difficult to diagnose a single cancer in early stage. So how cancer develops? So like we know our traffic rules. So we have green signal to go, red signal to stop, and orange or yellow to slow down or look everywhere. So our normal cells, they follow the same protocol. So they grow, they replicate. Some cells, they replicate very fast. Some are very slow. And some die on time. Some take a long time to die, or we call it is apoptosis and other mechanisms in cellular level. While now this is a cycle for normal cells, while cancer cells, they don't follow it. When there is a genetic changes in the normal cells, the changes in the DNA, they cause some defects in normal cells, and they start to overgrow in a very short period of time. And they don't follow any protocol for our normal cells. So they grow very fast. They don't slow, they don't stop. And they grow and grow. And that's the cancer. So it's not coming from outside. It is intrinsic property of our cellular. It's just because of the defects in DNA. And there are many parameters who makes the defects. We call it is a carcinogenesis process. Well, normal cells, they have it depends on which cells, like our lung cells, they grow fast and they die too. Our skin cells as well. Our brain cells, but some brain cells, they don't grow fast, they don't die fast. So it's depend on the cells, but generally cells have their own cycles. Cancer cells, they have their own cycles as well. So in laboratory level, within 2 or 3 days, we can grow the cancer cells. While in human body, it takes 2 to 6 weeks from one single cell to some million of cells. And they then come to the overgrow condition and the tumor. So at the end, we get a tumor. So while cancer has different types in men, they have types in women as well. So cancer has like skin cancer, we have blood cancer, lung cancer, kidney, prostate. While in men, the lung cancer is highly dominant, and in women, the breast cancer is highly dominant. So we are working on the breast cancer, and right now in the brain cancer. So what we are doing actually, right now, cancer therapies, we can treat the cancer with different therapies. So most famous is the chemotherapy and radiation therapy. While they have their own side effects, chemotherapy has the most side effects. Chemotherapy drugs, they target the overgrowing cells, and unfortunately they are not systematic. So they go everywhere except the brain. They go in our heart, they go in the kidney, they go in the lungs, liver. And unfortunately, at the same time, they make their side effects on different organs. And this is a crucial part in cancer therapy. Radiation therapy is not so, don't have many side effects, but unfortunately, its efficiency is very low, and we can't target many cancer. Like we can't use the radiation therapy for lung cancer or some cancers in kidneys or liver cancer, because they make more damage than the cancer. Surgery is the most option for cancers. Those are accessible to remove from the body. But unfortunately, most of the surgeries are very difficult, like brain cancer, where we are targeting now our approach. So it's difficult to make the surgery. Even in brain, if we just miss 1 millimeter of normal brain, we can make damage in our nervous system. Patient can get a paralysis, patient can lose the memory. So this is very crucial and difficult task for surgeons to do the surgery for brain tumors. And that's why now world is now focusing on the very systematic approach of the cancer therapies. That is called the targeted, and where we are now focusing. So we are designing the nanomedicine branch, nanotechnology combined with the medicine, and we are using the physics as well. So what we are we are working on different nanostructures, like chemistry has branches, organic, inorganic, physical, and others. So we have in the nanomedicine also the same branches. So we have some organic nanostructure like proteins and polymers, liposomes. Well, we have inorganic as well. So like magnetic material, where our strategies, gold, silica, carbon, some carbon nanotubes. We have organic, inorganic hybrid structures. So they are combining the biomolecules with the inorganic materials. And this is a very novel approach. So where we can combine the different properties together and we can achieve the highest efficiency in therapy or in diagnosis. What we are doing, actually we are working with the specialists in hospitals and biomedicine field together with the physics people and chemists as well. So our group is specialized with chemistry and physics and medicine people, where we are focusing on different strategies for cancer therapy and using the chemical laws, physical laws, and biological properties. So our more focus is on the hyperthermia or ablation of tumors directly using the heat as a physical energy, but using the nanoparticles means these are the chemicals, and we are killing the tumor means we are dealing with the biology. So combining three streams of the science together, we are designing the very, very specific nanoparticles. They are made up with the polymers, they are made up with the gold, they are made up with the magnetic materials, there might be a silica materials, and some carbon materials as well. We are using not only just chemical properties, but we are focusing on the physics as well. So in physics, we treat with the energy, and energy comes from different sources. So we are using two different energy sources. First is the magnetic field, and second is the light. And they are natural. We know, and they are not harmful to our body. So light, except the UV light, the near infrared and visible light is helpful to our body. Even in near infrared has more benefits than the visible, because its penetrating depth is higher, so we can go some tumors, like we can treat some tumors in livers, tumors in the kidneys, even brain tumors as well. And some visible light has limitations, so we can deliver the nanoparticles using the biomolecules. They are chemicals and very targeted, like aptamers, like DNA molecules, or like proteins or peptides or antibodies for the delivering these nanoparticles to very specific tumors, and then excite with using the light and magnetic field. So what is that? So I will come to our strategy, what we are designing. So it's just one example of our research. We have more than 50 publications in this field, and we have 3 inventions. So at the end, I will come to the part of invention. What are it is different than the patent and just publications. So it's a simple. I will give you the simple example of our research, how we are dealing with the physics, chemistry, and biology together. So graphene, you know. So it is a chemical. So it is made up of with the carbon, but have a very different structure. So we are functionalizing graphene with some materials like silica-based materials. So they can be charged, and then we are doing the magnetic materials, functionalizing it with the magnetic materials, so we can achieve the magnetic properties of graphene, because graphene is not magnetic, it's a paramagnetic material. So we are making ferromagnetic graphene structure in a nanoscale, and then we are using some polymers to attach some biomolecules like drugs and aptamers on the graphene. So it can be assembly used for the chemotherapy, let's say. So graphene, why we are using the graphene? Because graphene has a high surface area than any other nanomaterial. So we can use as a multifunctional material. We can combine it with the many other materials together, and biomolecules and drugs and targeting agents. So we have made the very, very specific hybrid structure with the graphene, and then we imagine how it looks like. So under the transmission electron microscope, you can see the graphene conjugated with the iron oxide. Even we added the gold on this graphene surface to get it excited with the light and magnetic fields together. Because gold has a light absorption properties and iron oxide has a magnetic absorption property. So we can trigger it in under two different fields. So we can see under the elemental mapping, graphene has conjugated with the iron oxide, magnetic metal, and it has a super paramagnetic properties. So we can excite under the magnetic field. And it has a very specific magnetic property that we call the super paramagnetic. Means these all materials can show the magnetic properties under only magnetic field. When we remove the magnetic field, their magnetic properties get down, or we can tune these magnetic properties. So this is more helpful when we target these materials inside the body and apply the external magnetic field. Then we can tune their magnetic properties and use these magnetic properties for heat generation or drug delivery. So how it works, like the material who has magnetic properties under a magnetic field, they can be attracted to the magnetic field, and under the magnetic field, they get magnetized. And when we use some alternating magnetic field, so they can be flipped. So like their directions will be changed. And this is very interesting property in the magnetization. Using this property, we are generating the heat in the material. So these materials then generate the heat. So we have designed the magnetic system. Coil, we call it is induction coil. We can generate the high magnetic field here. So under this high magnetic field, these materials can be magnetized, and using the high frequency, we can get the alternating magnetic field. And this alternating magnetic field generate the heat, not only generating heat, but it can be used to deliver the drug inside the cell. So how we did it? Also, parallelly, we have designed the laser system. So this laser system can be active under the magnetic field and the light. We can be achieve the more efficient properties by this material, or we can trigger this drug release inside the tumor, not only using the magnetic field, but using the light as well. So this is a multimodal approach. And very, very specific approach to achieve the high efficiency of this therapeutic part. So we design using the electronics and computer engineering together. Even now we are using the artificial intelligence and machine learning platform to optimize this system on more application level. So I will give the example how this works. So these are the cancer cells. These are the colon cancer cells, very specific drug resistance cancer cells. And we use this platform, hybrid platform made up with the graphene magnetic material conjugated with the drug. So this is a model drug. We use the doxorubicin is anti-cancer drug. So this drug we have targeted to the cancer cells using the biomolecules like aptamers. And they are very specific to the cancer cells. They are delivering inside the cancer cells, and not just going inside cancer cells, but they are delivering the drug. While when we apply the magnetic and light together, they are delivering the drug very high efficiently than the without field. So these fields, magnetic and light, these are energies as well. So they are triggering these all drug release inside the cancer cells. So we design this protocol So we combined the magnetic instrument with the laser system, and then we found the effect. And we did on the animal or in vivo level as well. Unfortunately, we have just filed the patent and we are waiting it's published. So that's why I did not include this data in the presentation. And we are working with, at the end, I will come to one of our collaborator from Switzerland, where we are working on very, very specific patients, not only just on the animals, but very natural patients, those have cancers like dogs and sheep. So we are exploring this technology on high level. We worked on the, not only just delivering the drug, but killing the tumor cells under the drug release and generating the heat by the magnetic field and laser. So almost in vitro, in lab, we have killed the 98% of cancer cells and almost 100% tumor in vivo level as well. So you can see here in the last row that these all cells looks like a red, means they are get killed by this our novel multifunctional approach. It's just one example of our system, but we have different nanomedicines and we have different protocols as well. Due to the time limit and to give the just a simple overview about what we are doing, I have just included a simple result so everybody can understand. But we are doing very in-depth level as well. So what we have designed very hybrid nano platform for cancer, and many people are doing it, not just we. But what is different for us? And I will come to that. So what different we are doing? So this is a common research that everybody is doing in the lab. What is the different for us? So we are commercializing. We are not just publishing papers or just making a fancy words. We are commercializing our research. We have technology transfer unit. We are identifying where is the level, our technology level. So in European Commission's regulations, every technology has their technology readiness level, we call TRL levels. And we are identifying what is our TRL level, how we can improve. So like 1 to 10, they are identified 1 to 10 TRL level. So we are around TRL 5, where we are almost to transfer our lab technology to the market. So with the help of our technology transfer unit, we have different units, not just technology transfer unit. We have patent department. We have IPR department. IPR is different than the patent. So we can take our rights by different way, just not a patenting, but we have take rights by just filling the forms by institutional level or government level. So we have our office, which is helping us to transfer our lab technology into the market. And we are analyzing market. So we have contacts in industries in Europe, in USA, where we are explaining technology and then identifying the market. So what we achieved with this? So just 2 months ago, our technology has been won the award, Innovation Radar Prize, which is given by the European Union. Every year they are giving one single prize for the highest technology, who developed the highest technology or transfer their technology from lab to the market. And we have transferred our technology using the laser, magnetic field, chemistry, biology, everything together. And it was one of the most successful technology last year. So we have competed around 35,000 participants or competitors across the Europe, not the globe, but it's from the Europe, around 1,500 universities, 300 industries as well. And our success story was published in many European news channels. It was published in India as well. And many news across the globe, not only in single language, but it was broadcasted in 15 different languages. Around 40 crore, that is 400 million households, they watched this news, and it was for 1 week in November. every day 4 times. And we have got tremendous response for our technology transfer. And we are now establishing our own firm in Europe, and we have registered one firm in India as well. Just recently, we got the permission of from Ministry of Corporate Affairs and Company Affairs. So, as a researcher, we have to be interdisciplinary, and just in this pandemic time, now just doing the research in the lab, it's kind of wasting the time of ourselves and wasting the money of taxpayers just doing the research. We need to be very specific now for technology transfer, and we have the group. So we have the group across the globe. He is helping us to deliver our research on the advanced level. So one notable group from University of Zurich, where we are doing the animal trials, even we are doing animal trials with an Indian university. We have a group from United States, we have a group from Korea, India, Ireland, Poland, from every corner of the globe. We have collaborators from highly authorized and highly renowned universities, and their expertise is different. So not from just from the same expertise. Like the group from Ireland, they are more on the technology transfer. The group from University of Zurich, they are more on the animal side. The group from India, they are more on the synthesis side or from the basic science. The group from US, they are on the hospital, they are helping us in radiology department. So we have interdisciplinary team as well. We are working together. So this is what we are doing and how we are exploring our technologies. In Oxford, actually, what we are doing different, we are working on the brain cancer of small children. And the problem with the brain cancer of small children, we call the pediatric oncology. The surgery is the only most or best suitable option because we can't treat them with our chemotherapeutic drugs. They have many side effects, and even radiotherapy, they have many side effects. So unfortunately, there are many limitations with these small children's tumor. And we can just go with the surgery, but surgery is very dangerous for small children. The problem is surgery is that we can't differentiate the boundaries between normal brain and the tumor. And in many times, surgeons, they resect, they cut the normal boundaries or normal brain section. And unfortunately, these children lost their memories, lost their many other body movements as well, because its brain is controlling everything. So, and it has everything there. So that's the difficulty. And we are using our Raman technology and the biology and chemistry together to identify the boundaries or the borders between normal brain and tumor. And we are designing the instrument and the cameras so they can be used in the surgery rooms. So this is our research approach here. And also we are developing some projects on how this coronavirus affecting the cancer patient and others. So at the end, I will come to the one quote by a German Prime Minister, who is a chemist. She has a PhD in chemistry, and who is now German President, Angela Merkel. So what she is looking more interdisciplinary scientists and leaders who has a scientific background. And this pandemic time, we need a leader who has a scientific background to deal with this. It's not just a bureaucracy where we can control such kind of pandemic. We need the scientists, we need the science to deal with this pandemic. So thank you very much for listening, and I would like to happy to answer your questions if you have. Thank you very much.
Thank you, sir, for nice talk about the cancer therapies in the modern science, which are related to the chemistry. As we know that the nano addition, in particular in the modern life, is a very valuable because they have more observable, and also they have the many advantages as the traditional medicine. So thank you, sir, for the informative session. So if anybody have a question, and they are also write on email, because we have a very short of time. If somebody ask, I will take up only one question.
Yeah.
Because we are running very late. Okay. So
Hello.
one question.
Hello.
Hello.
Yeah, this is Dr. Sahi Thorat. I want to ask one question.
Okay. Okay.
Hello.
Yes,
Hello.
yes, please.
Yeah,
Yes,
yes,
yes.
sir. This is very nice lecture, very enthusiastic work. It's very impressive. I have one query that you are using both laser and magnet together. Okay. So what is the laser intensity you are using, and how much time you have given that laser?
So in terms of intensity, generally in our field, we are measuring the power. So we are
Yeah.
dealing with the power of the laser. So it's a
Okay.
very, though it is high, we are using the 1 watt maximum, but starting from the 100 milliwatt to 1 watt. So we are optimizing as well. And it is time also we are optimizing from 10 minutes to 30 minutes, not exceeding the 30 minutes, because we can't treat this therapy. It is an ablation, so killing the cells by using the
Normal cells
temperature.
also.
So
Yeah.
we can't use it for longer time. Like
Yeah.
our radiotherapy, we can use for 5 minutes maximum in hospitals. So
Okay.
patients have to go every day for radiotherapy for 1 month or some protocol. So, but our approach is we are trying to do it with using the different nanoparticles, nanosystem, and technology together. Also, we are introducing now artificial intelligence. So, how we can optimize the time and the laser intensity, or let's say the power.
Okay, sir.
Okay, sir.
Thank you, sir. Thorat sir, thank you, sir, for your nice and informative lecture. We are very thanking to you on the behalf of organizing committee and myself, because you have given our very informative lecture on the nano editions area. And we have your email ID, and we are also thankful because you are joining us on my request. Because these days there is a 25th December and Christmas, and also the New Year holidays are there. So thank you, sir, for joining us.
Yeah, I have just one simple question that I missed, though you are running late with the time. So everybody, all listeners are maybe curious to know about the vaccine. So when it will be coming. And so I would say just wait for the next. Definitely Oxford vaccine will be get approved here. Probably we are waiting to get the good news today or tomorrow. The Oxford vaccine will be approved in UK. And once it will be approved in UK, I'm sure Indian government will be approved just 1 week or 2 weeks later. So it's all done. And for the India, we have the only hope from the Oxford vaccine, because it is we already have the infrastructure. And unfortunately, maybe today or tomorrow, the Times of India will publish my article on the progress of the Oxford vaccine. But I belong from the Maharashtra, so all media in Maharashtra, TV media, I'm writing every week a Marathi article in the Maharashtra newspaper. Dainik Bhaskar will publish my article on the Oxford vaccine as well. So stay tuned with the media as well, because we scientists believe this is a time where we can spread the correct knowledge, scientific knowledge to the society. And I also request all participants who has a scientific background, it doesn't matter you are from which background. It matters how we can spread the correct scientific knowledge to the society. Though I'm in Oxford, but I belong from very small village and small college, and I did my PhD even in India in very small university. Many of here from IITs. I am not an IIT alumni or somewhere, but you can achieve more. It doesn't matter where you are. So thank you very much. And now I'm handing the session to you.
Okay, sir. Thank you, sir. Now I am inviting to our next notable speaker, Dr. Nem Singh. He is Dr. Nem Singh is joint PhD in the Department of Chemistry, Indian Institute of Technology, Delhi, with Professor Anil Jayas, the synthesis and asymmetric catalysis. Afterward, he moved to Department of Chemistry, the University of Ulsan, South Korea, on the prestigious Government of South Korea NRF Fellowship, where the work of anti-cancer and drug delivery application of coordination-driven self-assembled supramolecular. Dr. Nem Singh also has 3 years of experience in photocatalysis and artificial photosynthesis with Professor J.O. Wang at Korea Research Institute of Chemical Technology, Daejeon, South Korea. His research has been published in more than 30 high-impact journals that include 2 Journal of American Chemical Society and 2 ICCAML. He also contributed to MRSC book chapter anti-cancer research and 2 international patents. Currently, he is working as a research professor of Korea University, Seoul, where he is working on the design and synthesis of anti-cancer and cancer diagnostic compound. So we know that the inorganic compound also the very valuable in the medicine area. So Dr. Nem Singh also our colleagues and senior. So I will invite the Dr. Nem Singh for their inviting term. Dr. Nem Singh.
Thank you so much, senior members of organizing committee, and special thank you to my very good friend Dr. Laxman Singh, with whom I worked in Department of Chemistry, University of Ulsan for around 4 years, and there both of us got the prestigious NRF fellowship. And after Dr. Laxman moved to India, and I moved to other institute, Daejeon, and from there I moved to Seoul in Korea University, where now I am working on nanoparticle-based cancer therapy, especially photodynamic therapy and photothermal therapy. But here actually I just started few months back, so I will now talk on my previous work, which I did in University of Ulsan. So today I will talk about some self-assembled supramolecules which are being used for cancer therapeutics, like in therapy and diagnosis. Both these supramolecules are playing a part. So currently I am working in the Korea University, which as you can see is among the top ranked university in the world, actually 3rd ranked university in Korea. And
sir, your voice is a little bit, so you please say loudly.
Oh, my voice is not clear?
Yeah, your voice is not.
Oh, actually I'm not using headphone. Can you hear?
Yeah, no, it's okay.
So I will keep my talk very, very short. So I will actually encourage everyone to ask questions about Korea, because in India everybody know about the European countries, Oxford and US universities, but I will encourage everyone to ask about Korea. As you see in this corona conditions, Korea is one of the country which fought very well compared to all the countries because of the technology, the modern research they are doing. If you see now, even the cancer research, Korea, if you do all the publications, Korea doing so well, Korea and China, and all the developed countries are actually lagging behind. So if you have questions, please ask. I hope I can answer. So moving on, I will talk here about cancer. As you know, the cancer currently, even in the time of corona, cancer is the leading cause of death. So now if you see, by WHO research, the 2 out of 35 cancers we have in 2020. So if we move after 5 years, we predict that there will be 7% of cancer out of 35, and moving beyond up to 2040, it will be around 25 patients of cancer out of 35 if the case is rising like this, and that we could not find the cure. So actually, currently the major treatment is the chemotherapy, which is not very much successful. As you can, these are the mainly chemotherapeutic drugs which are being used. In our previous talk, we have seen mainly the therapy in some biology and physics part. I will concentrate more here on chemistry part. So I hope you will get some new information on the this part. So you see, these are all the chemotherapy drugs which are being used for chemotherapy. But the problem is the cancer is not like other disease where the drug does not need to reach the site of the disease. But in the cancer case, the drug should reach to the cancer, then only it can cure. But these small molecules, they actually, so like when cancer at a certain stage, this is like a fire. We need like fire trucks to reach very soon and cure, because as in a previous talk we have seen that it goes really, really fast. Within weeks it can the cancer cell increase at a very high speed. So the problem with the cancer, with the chemotherapy drugs are when we give a drug and it got filtered out by kidney, then we need, the drug is not enough, it is not reaching to the cancer site, then we give another dose. Then there is, the drug is rate increased, but it is again filtered out, and we keep on increasing the dose. But by that time, it became enough to kill the cancer cell. It can become more toxic than it can cure the cancer cell. So that is the problem with the chemotherapy drugs. That's why it is not successful in most of the cancers. So the solution for this problem is we find out the problem. Cancer drugs are not reaching to the tumor sites. The solution is in the big molecules like supramolecules or nanoparticles. What advantage of nanoparticles are by the EPR effect. And the nanoparticles, if the size is around 100 nanometer, it does not get filtered out by kidney. So it circulates in the blood for a very longer period of time, and like weeks, 1 or 2 weeks. If the nanoparticles are stable, it can reach to the cancer site because of the recently find out this EPR effect. At the site of cancer, the gap between there are a larger gap in these skin walls. So the nanoparticles or drug inside the nanoparticle can move towards the tumor and it can act what it's supposed to do. So that is the advantage with the big molecules, supramolecules and nanoparticles. So I will actually talk about some chemistry principle about how the supramolecules and the organic nanoparticles are formed. So principle of these supramolecules is like thermodynamic control. The reactions are controlled by thermodynamic stability of the molecule. So these molecules actually very low energy molecules. They are stabilized when the two building blocks meet, and they actually make some smaller supramolecule. Then they mix and they correct in between because of the energy. When energy high, it will correct, and when it will reach to the lowest energy, it will form a supramolecule. So these are some of the example of the building blocks you are seeing. Mixing these two building blocks, as you can see in this figure, we can make a supramolecules. So the use of these supramolecules is not only for therapy, but in diagnosis also. In the recently published this paper, actually this supramolecule has a property of when you radiate with light, in the presence of oxygen, it has a different color, but in the absence of oxygen, it has a different color. Like when it is like weak red color, when in the presence of oxygen, and in presence of oxygen, in absence of oxygen, it is dark red color. So the tumor, as you know, has insufficient oxygen. The oxygen is very less. So when it reaches to the cancer cell, because of lack of oxygen, it changes the color. So the supramolecule can easily find out. We can easily see this is a cancer cell and this is a normal cell. So this is how it works. I already explained this. So moving on to my work, I actually started this work making supramolecules in two simple molecules. Here now can understand much better how supramolecule can form. So these two simple building blocks, but in simple room temperature reaction, you can just stir, then you can get this kind of supramolecule. These were characterized by NMR and X-ray crystallography also. and we got a very good IC50 value for these supramolecules. So what actually these are the two-dimensional supramolecules which cannot carry a drug. If your purpose of the supramolecules is carrying a drug, is then we need to have a porous, or we have a gap porous pore volumes which can carry drug molecules. So we designed and work on these kind of molecules. Although this particular molecule was not used for the drug carrier because some stability problem, but still was published without anti-cancer studies. So not only, but this compound was tested for the IC50 value, which got some good IC50 value compared to the chemotherapeutic drug. And so supramolecules are not only useful for the just cancer detection, but the interlocked structure can be used now in like any virus. They mostly have interlocked structures. So basically, when the structure of these biomolecules, big biomolecules, proteins, or the virus and some bacteria, even they have mostly interlocked proteins. So what basic structure, to understand the basic structure, we need to go to the interlocked molecule like this. So because this molecule was first characterized in solution, so it was published in a very high impact factor journal. So there is no limit for actually the interlocked structures. So another interlocked structure was published by our guru, the Solomon kind of link. So different kind of links were found out and characterized for the first time in solution, and then we successfully published in the high impact factor journals. Actually, this how we characterize this. At that time, there was a new technique. Nowadays, many papers are already published, but that was the first time when we. This was the first work which we did. We characterized these the gas inside the cage. The gas, like this is an experimental gas. In place of this gas, we can have a drug molecules. So this molecule, you can see the large cyclic cage, which has a large pore, which can inside which we can add some drug molecules or gas or some fluorescent molecule to identify cancer cells. So this was the first time when we sequentially added the gas inside the case, and one by one we could characterize by in the solution by NMR, and by titration also we see sequential addition of the gas, which one was coming out, another was going in based on the interaction and the weak forces, and this gas was characterized by 2D NMR also, and then we characterized encapsulated gas in solid state, which we proven that this gas does not come out in the solution so easily. So it can actually take the drugs towards the cancer cells, tumor sites, without decomposing in between. So another example, we were successful in by dilution or by addition of water or addition of gas, we were successful in transforming the structure of interlocked molecule like this. And all these studies were characterized by, I'm not actually describing all this. If someone is interested, please ask me a question. I will keep my talk very brief. So if somebody is really interested, please ask me a question if you have any about this work. Otherwise, please. So in another example, in the very first 16 crossing knot, we synthesized this knot. Actually, these are the first time we find out these molecules, which are very much helpful in finding out the structure of like viruses like coronavirus. This kind of study in the background of if we could not have such kind of development in the science and chemistry, we could have never find out what is the new corona and how we can treat and how we can design a vaccine for that. So this kind of study plays a very vital role in characterizing in the new viruses especially. So that's why this work was very, very significant. So published in a very high impact journal. So we actually developed a strategy to synthesizing these this kind of interlocked molecules, and in this paper we standardize it, and we see the changing the condition and building block angle of the building block. We can synthesize whatever we want. We can synthesize that kind of molecule. So these were also characterized by solid state analysis. And here in current lab, I'm currently working on chemotherapeutic drugs, like all the therapy and photodynamic therapy and imaging, but I'm not presenting this work because I'm here just new and most of the work is unpublished. So I shortly concluded my talk only because please ask some question about Korea and this work. And I think I will be very happy to answer a query, especially some young students which are listening our talk. Any inquiry about, because Korea have many very high ranked university, and all the high ranked universities, no university is higher than this. In India, even not in 100 ranked universities there. So if you want to go for high ranked universities, it does not, like if you want to prefer US or Europe, you can come to Korea also. If you're interested, if you read about this, you will find a very interesting place. Very modern research is going on in Korea. So if any student is interested, I can help you. Thank you so much.
Thank you, sir, for joining us and give the very nice talk about the nanomedicine and macromolecules which are useful in the medicine. So we are just say that Dr. Singh say that the Korea also have the top most university in all over the world. They have also the most innovative, and they have the very less population, but they have a very large innovative technology. We are using a lots of technology in India also, like that in most of the metros and Samsungs and most Hon'ble and LG. These are the three most important companies from the South Korea. So that's why, thank you, sir, for joining us. Anybody ask any question? If someone want to ask any question, then we have invite another question. Okay, sir. Thank you, sir, Dr. Nem Singh, for giving the informative nice talk and joining to us. I am thankful to you on the behalf of organizing committee and myself. So thank you, sir, for joining us.
Thank you so much.
Now I am introducing another speaker is Dr. Rabindranath Lo. He is working as an associate scientist with Professor Pavel Hoza at the Institute of Organic Chemistry and Biochemistry, Academy of Sciences of the Czech Republic, Prague. He obtained his PhD in Theoretical and Computational Chemistry with Dr. Vishnu Ganguly from CSIR, CSMR, CRI, India. His main research work focused on the theoretical and computational description of non-covalent interaction and their role in chemistry, biodiscipline, and nanoscience. Currently, he is working on the importance of non-covalent interaction to tune the electronic and magnetic properties of metal phthalocyanine complexes. So, thank you, sir. So, Dr. Rabindranath Lo, I am inviting to you. Please, sir. Join us.
Yes, thank you very much for the introduction, and heartiest congratulations to Dr. Laxman Singh and Dr. Bipin Kumar for organizing such a nice e-conference. And so today I will talk about the non-covalent interaction and stimulated the spin state of metal complexes. So this talk is slightly different from previous two talks. Here we are not focusing on the nanomedicine. Here we are focusing on the nanoparticles, nanosensor, and some memory units. Uh, uh, so first, spin crossover complexes. So spin crossover actually is a transition of spin that involves the interchange of spin, like low spin to high spin or high spin to low spin. And this spin crossover is observed in the first two transition metal complexes with D4 to D7 and configuration. And this spin transition is mainly observed in presence of some external stimuli, something like temperature, pressure, magnetic field, electric field, or some covalent or direct bonding. And so, previously in 1931, so Camby et al. First observed this spin crossover in iron silide carbonates complex. And that time, Pauling actually initially explained these results as the change of bond type from covalent to ionic. But Orgel first explained this behavior as the change of spin state of iron center. And interestingly, as a consequence of in 1950s, this ligand field theory established, Mosfet effect discovered, and then spin crossover explained. And as a result of this spin change, there is a magnetic interaction and bulk magnetization observed. So here is a classic example of thermal spin crossover complex. In the left side, this is iron phenanthrolene complex, and it exists low spin complex, and at whatever temperature you are using. So at high temperature it is low spin, and at low temperature something 5 Kelvin, there also it is low spin. But if we replace one phenanthrolene ligand by two isothiocyanate ligand, then it changes to the spin state. So at high temperature, something like 300 Kelvin, it shows high spin complex. And if you reduce the temperature, then it changes the spin state. And at the low temperature, it shows low spin complex. And it was observed that at temperature 175 Kelvin, and this spin crossover occurred. And as a result of this spin transition, there is changes in geometrical orientation, magnetic property, electric field, and refractive index, color of the molecule. So that's why this spin crossover molecules or complexes used as a electronics, spintronic devices, sensor, nanostructure, hybrid materials, memory units. So it has a widely application. So our motivation is to control the spin state of single molecule, but not the external stimuli, something like light, electric field, or covalent or direct bond, but with non-covalent interaction, and also tuning the chemical reactivity of graphene. So in these purposes, we have taken iron thiocyanine molecule, and this iron thiocyanine molecule is widely used as electrocatalysis, magnetic switching. And the beauty of the molecule is that it can stay in different spin states, so low spin, intermediate spin, and high spin. And here iron is +2, so D6 system. So, so as I mentioned that iron thiocyanate present in different spin states. So when it is in quintet state, there is 4 unpaired electron, and this dx square minus y square orbital is singly occupied when it is when the electron is flipped to dxy, dxz, or dyz orbital. Then this dx square minus y square orbital is vacant and it is high in energy. So in that case, it forms a singlet state. And when that spins, when the electrons from dz square orbital is vacant, then it forms a singlet state. And this electronic tuning is done previously by pressure, temperature, or impedance of light. But in our approach, we have taken a surface to tune the electronic structure of iron thiocyanine molecule. But before going to spin crossover, we need to know the exact spin state of iron thiocyanine molecule in ground state. So actually there are lots of studies are reported on iron thiocyanine molecule, and mostly they explain it as a triplet ground state because the FEN bond distance is very close to triplet one. And but most of these experiments are done in high temperature or and in a crystal structure, it form a layered structure. So it's really hard to get the isolated iron thiocyanine molecule, and also it self-assembles the system, and sometimes it interacts with the surface. So as I mentioned that all these external stimuli can change the spin state of molecule. So it's really difficult to predict the exact spin state of iron thiocyanine molecule. So a reliable determination of its ground state is still challenging. So in these purposes, we have used various DFT functional, and in the table you can see various DFT functional are used, and in this case we got triplet as the most stable compared to the other spin state singlet and quintet state. So, which corroborate with the previous results. But we need to know the exact spin state, so we are using some high-level calculations on multi-configurational SCF methods, and this method shows that that in CASPTT and DMR calculation, it shows that iron thiocyanine molecule exists as a quintet state, and which is further greater stability than the triplet and single state. So we need to confirm this observation by experimental support. So our experimental collaborators, they perform mass spectroscopy in a frozen chlorobenzene medium, because in the frozen chlorobenzene medium, it is supposed that this iron thiocyanine molecule exists as a isolated state, like in gas phase. And so the mass spectroscopy shows that when it is in crystalline form, it is there's quadruple splitting is 2.53, and when it is in chlorobenzene media, this is quadruple splitting is larger. So in that case, they assign that when it is in crystalline state, it is in triplet state, and when it is in chlorobenzene medium, it is quintet state. And so we need to know whether in chlorobenzene medium this iron thiocyanine molecule exists as a isolated or not. That's why they perform this wise temperature, and the geo-wise temperature supports that this iron thiocyanine molecule exists as an isolated state. It is not interacting with other iron thiocyanine molecule. So our multi-reference calculation clearly proved that this ground state of the isolated iron thiocyanine molecule is quintet, which is further correlates the experimental results. Now we need to see the spin crossover of iron thiocyanine molecule. As Dr. Thorat already said that the graphene has a large surface area. So in this case also we are using graphene as a surface. And also we are using the nitrogen doped surface. This nitrogen doped in experimental condition, they are using these nitrogen ions and bombard, and this they are getting this iron, this nitrogen doped graphene surface. It has improved conductivity, transport features, and this performance actually governed by the nitrogen concentration and its local environment in the graphene, so that it is so we can get pyridinic, pyrrolic, or graphitic nitrogen doped graphene. And in the picture you can see that the brighter spot, that is the presence of nitrogen atom in the graphene surface. So when this iron thiocyanine molecule is absorbed on a pristine and nitrogen doped graphene, we got two different scenarios. On pristine graphene, and in pristine graphene, it's from a large well-ordered flat island, whereas in nitrogen doped graphene, this iron thiocyanine molecule, it stays in a single molecule or small cluster molecules. And so now we need to explain this two different behavior. So we have taken, we cannot take a whole graphene surface, that's why we have taken some model systems, circum coronae, and which is a model system of graphene. And if you replace one carbon atom by one nitrogen atom, it is formed a graphitic nitrogen defect. And further, we have extended our studies with para in defect, where two nitrogen atoms are there, two doped nitrogen atoms. And also another possibility is that it's a pyridinic type of in defect. So this all surface we have considered, and we have observed iron thiolocyanine molecule over it. And the optimization shows that this iron thiolocyanine molecule, there is no direct bond between the surface with molecules. So it is bound with a non-covalent interaction, and the interaction energy is quite high. And for these two cases, and but when it is nitrogen doped, it is interaction energy is more compared to the graphene surface. And interestingly, in iron thiolocyanine molecule, on graphene surface, it can freely move over the graphene surface, and but there is no restriction. But in nitrogen doped graphene surface, this iron thiolocyanine molecule stays near the nitrogen atom, and there is a energy barrier required to prevent the lateral motion. And interestingly, this we initially we thought that this nitrogen, this iron atom in iron thiolocyanine should above the nitrogen atom, because we are using in dopant. And but the geometry shows that there is a non-centric absorption of position of iron thiolocyanine molecule, which is further seen from the STM images. And this red dot is position of the nitrogen atom. So this iron thiolocyanine molecule is slightly shifted regarding the nitrogen atom. And now we generate the electron density map, and it shows that when iron FePC molecule stays over the nitrogen doped, then there is a electron density, and this red color indicates the more electron dense in this molecule compared to the graphene surface molecule. And the STM images also shows that when an iron thiolocyanine molecule is near to nitrogen doped graphene, it is more brighter compared to the graphene surface. So now we need to explain this behavior. So there may be charge transfer from surface to molecule, which reflects in the electron density, or maybe some local electric field, or some mixing of hybridization. So in DFT study, we have seen that when iron thiolocyanine molecule is in graphene surface, it is in triplet state. So there is no change of spin state. But when it is in nitrogen doped graphene surface, then there is a change of spin state, and it becomes a singlet state. So now, as we already mentioned, that maybe the charge transfer, it involves with the spin state change. So we have generated the electrostatic field of this surface, and the surface shows that this nitrogen doped graphene surface actually is slightly positive side, because this extra electron on nitrogen atom is delocalized over the surface, and the center near to the nitrogen atom is slightly positive. So and this homolumo is far from the Fermi level, so there is no partial charge transfer. So that's why we have run constant DFT methods, and here we restrict the charge transfer between the surface and FePC molecule. In this case also, we found that there is still spin change of iron thiolocyanine molecule when we restrict the charge transfer. So that means this charge transfer is not responsible for this spin change. Now we examine the role of local magnetic field, and so here we have taken two nitrogen defects in para position, and this optimized structure shows that in this case there is no change of spin state. So which is further confirmed by the STS spectroscopy, and here the electronic structure of the FePC molecule is remain intact. Now the experimental group observed this AFM structure, where they observed two types of iron thiolocyanine molecule in the surface. So when iron thiolocyanine molecule is in nitrogen doped graphene surface, then there is a square. When it is graphene surface, there is a and cross type structure. And in our calculation also, we shows that when this iron thiocyanine molecule is in singlet state, then there is a square type structure. But when it is in triplet state, there is a cross. So in DFT study also we have seen that, and when this iron thiocyanine molecule in singlet state, there is a depression of electron density over the iron atom. When it is in triplet state, there is no change. So that means so when FePC molecule absorbed on graphene surface, then it is a triplet state, and when it is absorbed on nitrogen doped surface, then it is a singlet one, which is further shown from the AFM picture. And also this singlet state in this case of a nitrogen doped, it is more stable than the triplet one by 5 kilocalorie. To explain this phenomena, we have generated the orbital structure, and it shows that when iron thiocyanine molecule absorbed on graphene surface, in that case, the dz square orbital is stabilized. But when it is in nitrogen doped surface, this dz square orbital, and which is along the z-axis, so it is destabilized. And we thought that there is intermixing between the orbitals with z component, that is pz of surface independent, and with interacting with the dx, dyz, and dz square like orbital in iron atom. So which facilitates the change of spin state from triplet to singlet one. So in this part, we have seen that nitrogen doped graphene surface is positively charged, and this graphitic defects can affect the cell assembly of FePC molecule, and it introduces the spin change through non-covalent interaction. And we have also seen the different para defect. But all these calculations are in DFT methods. So, but we need to know the results with the high-level calculation like multi-comparison, multi-reference methods. And as the size of the graphene surface and FePC molecules, so we cannot use the high-level calculation. So for that, we need to know, we need to go for a small systems. So in that case, we have taken iron porphyrin molecule, which is representative of iron thiocyanine molecule without the 4 phenyl groups. And in this case, we have used different DFT functional methods, and all these functional, it shows that the triplet state is more stable than the other two states, singlet and quintet state. And in CASSF and CASP2, the quintet state is more stable than the other spin state, which is also observed for the iron thiocyanine molecule. Now we need to create one surface which is interacting with the iron porphyrin. That's why we have taken only benzene molecule and NP radical. So this benzene is representative of graphene surface, and this NP radical is representative of endopent benzene. And here we have seen that in both cases, in DFT and in multi-reference system, triplet state is more stable compared to the singlet and quintet state. And when pyridinal radical is present, then singlet state is more stable compared to the other two states. That means, so we need a valence electron in nitrogen so that it can change the spin state of the molecular orbital. So here this orbital occupancy of isolated FePZ and its complexes. So in isolated state is quintet state, so 4 unpaired electrons are there in dx square y square, dxz yz, dxy. And dz square orbital is more stable compared to the other. And when this FePZ molecule is put on benzene, then and this dx square minus y square orbital becomes empty, and it becomes a triplet state. And if we interact with some endopent, in that case, this feature of endopent is interacting with the dx, yz, dx square, and in this case, this dz square orbital is empty, and so it becomes inlet state. So as a conclusion, we can say that these iron molecules, iron halogen, iron porphyr is when it is isolated is a high spin complex. So when it is interacting with the benzene, then it is becoming a intermediate spin, and when it is interacting with CO, some covalent bonding, then and when it is open cell non-covalent interaction, then it becomes low spin. And such non-covalent tuning can also available for nanotechnology, electronics, and magnetism. And so I would like to thank Professor Hofza, the group leader, and Anand Devaste, and also our experimental collaborators, Radhe Gosin and Pavel Elini. And it was a nice collaboration and excellent. And this is our institute and funding agency is Gacher. And thank you.
So thank you so much, Dr. Lo, for joining us and gives us a nice and informative talk on the inorganic complex. As we have noticed that our today's talk is very informative, and these talk are very important in the area of nanoaddition. So participants mute their mic because there is a noises in background. So Dr. Lo discuss about the how nanoparticles and how complex are valuable in the medicine area, in particular the cancer, because we know that the cancer is a deadly disease and we have no such treatment for in early stage or later stage. If these complex compounds, these nanomaterials and these nanoparticles which are valuable for the patient, and we can stop this cancer disease early in stage, it is very fruitful. So thank you, Dr. Lo, for joining us, and I am thanking you on the behalf of organizing committee and myself. So now I am inviting to our principal, sir, Professor Bipin Kumar, sir, who is the principal, and please, sir, giving the closing remarks of this international e-conference. Professor Bipin Kumar, sir.
You for attending this international conference. I congratulate Dr. Laxman Singh to organize such a nice international.
Sir, your video is not on, sir.
I am not audible?
Yeah, you are audible, but your voice is very little low.
Oh, okay.
Okay, sir. Nice.
Thank you to all of you for attending this international conference. I congratulate Dr. Laxman Singh to organize such a nice international e-conference jointly organized with Department of Chemistry, Patliputra University, Patna. The main aim behind organizing this international e-conference on chemistry and its application in modern life, ICCAML-2020, is beginning the most eminent researchers, scientists, industrialists, chemical analysts, materials chemists, industry innovators, and entrepreneurs on the same platform of new innovation, which will show the world a new age in evolution in materials. The conference got off to an excellent start with the keynote speech of Dr. Nanasaheb Thorat, Marie-Curie research scientist, Oxford University, UK. Dr. Nem Singh, research professor, Korea University, Seoul, South Korea. Dr. Rabindranath Lo, associate scientist, Czech University of Sciences, Czech Republic. I am happy and show my gratitude to our Vice Chancellor, Sir, Professor Jaisawal, for patronizing this international e-conference, and also our college, faculty members, and non-teaching staff for their cooperation during this event. I also show my gratitude to our eminent and notable international speakers have been delivered the lectures in the field of not only in the field of chemistry. They have the cover wide range area of biology, physics, and environmental field. Interesting topic. There are lots of technological examples which are widespread application of chemistry, like use of touch screens enabled by plastics, adhesive, and other products of chemistry are employed on cell phones, PDAs, computer screens, and more. Thinner screens soon will be applied to windows, consumer products, and public displays to enable increased in interactivity and commerce. In everyday life, the chemistry is found everywhere. There are lots of examples, such as in human body. The digestion rely on chemical reactions between food and acids and enzymes to break down molecules into nutrients in the body can absorb and use. The soaps and detergents act as emulsify to surround that and cream so it can be washed away from clothing, dishes, and our bodies. All the drugs work because of chemistry. The chemical compounds may fit into the binding site for natural chemicals in our body. I thought with a large number of participants, we are sure that this e-conference will be a memorable, highly educational, innovative, informative, and not to be missed event. We hope that this conference will help you better understand the subject of chemistry and obtain the knowledge necessary to improve the state of the subject in our country, especially the state to get ideas for the projects, sponsors, agencies in India, DST, DBT, and ICAR. We truly value your participation and support for this conference. I am thankful to our HOD of Chemistry, Patliputra University, Dr. Ashok Kumar Gupta sir. I am giving my special thanks to Dr. Laxman Singh, and I request Dr. Laxman Singh to say a few words in last. Thank you.
So thank you, sir, for appreciation. And this conference is successful on the behalf of Department of Chemistry, Patliputra University, and our college jointly organized this conference. I also thankful to Professor Ashok Kumar Gupta, presently as a HOD of the Patliputra University. And we are very thankful to all the participants who has joined us, and we are also thankful to our notable speaker, Dr. Thorat from the Oxford University, and provide the knowledge about the nanomedicine and nanoparticles, and he also gives such a nice information and a good news about the Oxford vaccination. And he said that in 1 and 2 days, the Oxford vaccine should be finalized in the UK. Then we have also got a good news in India within a week, almost in the first week of January. And also we have also thanked to Dr. Nem Singh. He's our senior colleague from the IIT alumni, and he also gives a nice talk on about the inorganic molecules. And his area also the inorganic molecule which are working in the macro molecules, and they gives this some goods compound like a ring formation, 6 ring, square ring. These are the molecules which are in the human body, and we have to take these molecules in a drug delivery system also in various mechanisms which are happening in our metabolism in our body. And we are also thankful to Dr. Lo, and he also some impressive talk on the magnetic and other material. And the today conference is mainly based upon the nanomedicines and other things, because we know that there is several deadly diseases like cancer and AIDS and other. Now that is a corona period. That is a deadly thing, is that corona also is a very bad news in 2020. But now there is a loss of strain this upcoming days. One strain, two strain, one from Ethiopia, one from Britain, and all of them, and we are also afraid about this new strain. The vaccine can we work or not, or vaccine decide. So in this conference, we highlighted the most of the themes on the these diseases, and how the chemistry and the basic chemistry is useful in the modern life, and how this our modern life would be changed. As we know that always in the area from the nanomedicine to pharmaceuticals, drug delivery system, there's a other area also is useful is technological area. As we talk about the technological area, there is a lot of things we are using nowadays, like as laptop, tablet, mobile phone, smartphone. These are the devices we are using every day, and in 24 hours we are busy within a smartphone. So what is this? In these technology and innovation, the chemistry also is behind in it, because there is a energy power sources in hand is like a supercapacitor, lithium-ion battery, and other form. So in 2019, on the lithium-ion battery, the Professor J.B. Goodenough and other firm got a Nobel Prize. So we know that how the chemistry can change our life. So even though in our body metabolism, the chemistry is a very important. So such a nice confirmation and conference about this invited talk, and we are also thankful to our Professor Jaisawal sir, our Vice Chancellor, who also talk about the how chemistry is related to our daily life, and he also gives us some news about the bananas. That means in Hindi we say bananas. As science, so we can talk about that. So we are thankful to all of you. And our Professor Jaisawal sir, Professor Ashok Gupta, HOD, and our principal sir, Professor Bipin sir. So thank you so all participants to join us. So about if you have any question about the conference, so ask me. Anybody have a query and question about the conference and other things? We have.
Please share feedback link.
Okay. We have provide feedback in WhatsApp group. Okay.
Thank you, sir. Thank you so much.
So anybody else? Anybody else who want to say about it? Yes.
Sir, Rama Shankar Singh want to say something.
Can I remove, sir? Can I remove?
Sir, it's a really wonderful webinar. I learned a lot. Though I am not from the science side, but I learned a lot of chemical effect in body and other things about magnetic. It's a really wonderful international conference.
Thank you so much.
Sir, this is a very wonderful webinar, but I have not received the certificate of the FDP organized.
Okay. You have to get a certificate within 7 to 10 days. Okay. Thank you so much to all of you for participation to join us. So now Rajneesh and on the behalf sir Gupta sir, we have to close, sir, and principal sir, we have to close now.
Okay, sir. Thank you.
Okay, sir. So we have to now close. So Rajneesh, please share the link and video on the WhatsApp group. Okay. Of the recording. Okay. Then now we have closed. Thank you so much to all of you to join us.
Thank you so much, sir.